Let's dive into multiple regression. That's just a regression that takes more than one variable into account, more than one feature. The concept is actually pretty simple. It's just answering the question, what if I have more than one variable influencing the thing that I'm trying to predict? So basically, I'm doing a regression that I don't just have one feature that I'm measuring to try to predict some value. I have many features that might come together. So for an example, that might be predicting the price of a car based on its many attributes. The car has a lot of different things you can measure that might influence its price, such as its mileage, its age, how many cylinders it has, how many doors it has, things like that. And you can actually take all of those into account and roll that into one big model that has many variables as part of it. Now, as often is the case in data science, there is some confusing terminology here. In addition to multiple regression, which is using multiple features to predict a single value, we also have the concept of multivariate regression. And you would think that would mean the same thing, but it doesn't. Typically, when we talk about multivariate regression, we're talking about not only having multiple feature attributes that we're trying to use to make a prediction, but we're also trying to predict more than one thing at the same time. So maybe I'm trying to predict not only the price of a car based on its mileage and age and number of doors, I'm also trying to predict how long it will take to sell it or something like that. That would be an example of multivariate regression, where we have multiple things we're trying to predict in addition to multiple features being used to make those predictions. Either way, though, the way we do it is actually pretty simple. So we can just have, instead of a single coefficient attached to some single feature variable, we can have multiple terms with multiple variables. So we can say that we can predict the value price based on some constant value alpha times some coefficient called beta 1 times your first feature, which, say, could be mileage, plus some coefficient beta 2, which might be multiplying with some other feature like the age of the car, plus beta 3 times the number of doors, whatever you want to do. And those coefficients are just measuring how important each factor is to the actual end result. Now, this assumes that all of your features are normalized going into it, so you can actually compare those coefficients together fairly. If they're not normalized, that coefficient will also be working to scale that feature into the final result as well, and that can also be informative. If you actually work out the values of beta 1, beta 2, beta 3, and whatever else you might have, that can also tell you a little bit about what features are actually important for your model. So if you end up with a very low coefficient for a given feature after things are normalized, that might be nature's way of telling you that that feature isn't actually very important for predicting the thing that you're trying to predict. And that can help you to simplify your model by eliminating feature data that you don't need, so that's a very useful thing. That's called feature selection, and it's often a very important part of building a good machine learning model. Now, all of this still uses least squares, so in our notebook we're going to use something called OLS. That stands for ordinary least squares, and it can handle multiple features like this. So we can still measure the fit of this thing overall using R squared, nothing is different there. And another thing that we need to point out is that this whole thing assumes that there's no dependency between these different features. Notice that I'm treating all these features independently with their own coefficients. So if there is in fact a relationship between these features, this model will not capture that. And this is actually an example of where that would probably be the case. For example, the mileage on a car would probably be highly correlated to the age of the car, and this model will not capture that relationship. In fact, you'll probably be just fine just using mileage or age independent of each other, but this could at least tell you which one of those is more important to keep. So with that, let's dive in and actually fire up a notebook and see how it works. There is something called the stats model package that makes things easy, and it offers the OLS model that we can just use to go off and make it chug away and do it all for us. So let's make that example of multiple regression real. Go ahead and open up the multiple regression notebook file here, and you should be seeing something like this. Now, to make life a little bit easier, I've uploaded a little simple cars Excel spreadsheet here to my website here, and we're just going to use Panda's read Excel function to load that directly into a Pandas data frame, so Shift-Enter. And if that fails, just try it again. Sometimes, HTTP connections can be a little bit wonky. So let's take a look at what we have to deal with here. We're going to use matplotlib to visualize these things. Let's actually import the columns mileage and price only from that Excel spreadsheet. And then I'm going to bucket it up by 10,000 range intervals of mileage. And we'll bucket that up between 0 and 50,000 miles on our cars. So basically, we're going to take all of the cars in this spreadsheet of Kelley Blue Book values. That includes things like the mileage on each one and the price that it was sold for, and bin those together into 10,000 mile increments. We'll then compute the mean for each of those bins, print it out so we have a good idea of what it looks like, and plot it so we have a feel of what that data looks like as well. Shift-Enter, and we'll see what happens here. All right, so you can see that we've bucketed things into mileage ranges, 0 to 10,000, 10,000 to 20,000, and so on and so forth, up to 40,000. And we have the average mileage value within each range and the average price for each of those ranges as well. And when we plot that, we can see pretty clearly that as the mileage increases, the sale price decreases, which is what you would generally expect. Now, if you actually go beyond 50,000 miles, things get a little bit weird. There's some outliers that actually mess up the data, but generally speaking, more mileage means lower sale price. Not too surprising there. So let's continue to use pandas to split this matrix up into the feature vectors that we're interested in. So remember, we want to do multiple regression. We want to try to predict the price not only based on the mileage, but also on other stuff too. So let's see what we got here. We can actually extract not only mileage, but also the number of cylinders in the car and the number of doors in the car. So that's going to be our feature variables. And typically, we refer to feature variables by large, uppercase X. And we refer to the thing we're trying to predict by a lowercase y, just sort of the convention in machine learning, if you will. So we have a bunch of feature vectors, 3 feature vectors, mileage, cylinder, and doors, that are going to be used to predict the value of price. Okay, that's kind of what we call our label data. All right, so the first thing we need to do is actually scale everything down into a comparable range. So we're going to use the standard scaler here and the fit transform method to actually convert all the mileages, cylinders, and door values into uniform ranges between -1 and +1. There's a couple of reasons for doing that. One is that a lot of models work best with normalized data like that, but it also allows us to compare the coefficients we end up with apples to apples, right? So we don't have to take the scaling of the actual numbers into effect. We can just look at the actual beta coefficients that we end up with and look at them and say, okay, this means that this one is having this effect relative to the others. So we'll go ahead and do that and print it out so we can see what our scaled feature data looks like. And then we will call statsmodels OLS function, passing in the label data, y, that we want to predict the prices, and the feature data that we're having the X vector here that contains mileage, cylinder, and doors features. And we will fit that data to a model and print out a summary of the model when we're done. So let's go ahead and kick that off. Bunch of warnings here we can ignore for now. Here's the printout of our normalized data. So you can see that all the mileage, cylinder, and doors information have been scaled into the range -1 to +1. So we can actually compare them fairly. And here's the actual summary of the model itself that it came up with. So that's interesting. You can see the actual coefficients here that ended up on each of the feature values. So basically the beta value that's multiplied with the normalized mileage data will contribute -1,272 to the final price. The number of cylinders is +5,000 some odd, and doors is -1,400. So that alone tells you a lot about the model, right? First of all, just the magnitude of these coefficients tells you that the number of cylinders is actually the most important feature for predicting the sales price, which is maybe a little bit surprising. Might be due to those outliers we talked about to some extent. And the more cylinders you have, the higher the price, so that's a positive coefficient. Whereas the mileage, of course, is a negative coefficient because the more miles you have, the lower the price. Interestingly, the number of doors is also negative. So the more doors you have, the lower the price. That's a little bit counterintuitive, but maybe that just means that sports cars sell for more money than 4-door sedans. I guess I can rationalize that. But again, it's a good example of where the math gives you some useful insights into the data that you have. So that's kind of interesting. So yeah, just remember those coefficients are going into an equation that looks like this. There's some standard, there's some constant value beta 0 plus beta 1. That's going to be the mileage coefficient. And beta 2, the one that we're using for the cylinders. And then beta 3 times the doors. So do we really have to do that the hard way? I mean, we probably could have visualized this data and gotten the same insights a little bit more simply. And I do want to preach simplicity. If you can figure out something easily, then do it. For example, we could have figured out ahead of time that the number of doors does not increase the sales price. It's not actually a very good predictor of the sales price. And we could just do that by grouping together all the doors data and taking the mean of the prices associated with them. So with just Y, which is, again, our price data, grouped by the number of doors, taking the mean for each group, we can see pretty quickly here in one little line of code that 2-door cars in our data set typically sell for about $23,000, while 4-door cars only sell for $20,500. Not a strong relationship, but a negative one regardless. So that just quick computation could have told us pretty easily that the number of doors is probably not a good predictor for making price predictions. Interesting. So how to actually use this to actually make a real prediction? Well, you just have to scale the input features that you're trying to predict for back into the same range that we used to make the model. So I can use that same standard scalar instance that we called scale, and call its transform method and just pass in the unscaled feature data to get them down to the range that we want. So let's say that I want to predict the price of a car with 45,000 miles, 8 cylinders and 4 doors. I could scale that down, then call predict on my model and with the scaled values and print out the results. So let's go ahead and do that. We see here that the final prediction worked out to be $6,315 for that particular vehicle. Cool, so that's how you use this. And by the way, if you need to get back to the original values when you do a transform, there's also an inverse transform method on the scaler if you need to get back to the values that you had originally. All right, so with that, as always, I encourage you to mess around and play with this data. Try like manipulating the input data maybe. Download that Excel spreadsheet to your local disk and load it from your local disk and manipulate the data. See if you can actually create a measurable influence of the number of doors on the price, different than what we saw. Maybe you can like find some more insight into how those outliers at larger mileages might be influencing our final results and messing up with our model. This is also a good example of where data cleaning becomes important because there are outliers that are affecting things. Anyway, have some fun with it. And why stop at 4 doors? Why not create some fake fabricated data for cars that have 8 doors and see what that does to your model? So go mess around with it, guys, and I hope that's useful. That's multiple regression in a nutshell. Again, it's just a simple concept. You're trying to do regression on multiple features at once using coefficients attached to each feature. And as before, those coefficients are just arrived at using ordinary least squares regression.